Julio a copy of my book, and he's going to sell it to each of you for $5. So here's a copy of the book, and you can pass it around or do whatever you want, throw it away or whatever. But you'll see as you go, pretty long book, and you'll see a lot of the same figures in the book as you in this class. I've got a chapter on unconventional reservoir shales and geologic modeling and things like that, but we're probably not going to get to all of those. But we got a chapter of geochemistry, and here's the title of the book. So you're all welcome to have the free copy. Just don't tell the publisher. They lose money when they lose the sale. All right, well, back to the multi-cycles here. This is the one I thought I was showing you before. Turned out to be the wrong one. But here's a sea level curve for an interval. Well, let me back up and say that most places in the world, except in where you have just very rank exploration, most places will have these sorts of charts. Either a consultant will have made one, or usually internally within a company that's got all the data to build these charts. So if you're going to explore in a new area in Bolivia, for example, and you want to know at what age you might find submarine fan deposits, you can go to this chart, and wherever you have a low stand, at that time, where you have a low stand deposit, that's where you would want to look for your, wherever you had a falling stage, that's where you'd want to look for your submarine fans. You wouldn't want to look at a time interval where you had high stand deposition. You wouldn't want to look for submarine fans then. Okay? So that's one of the ways in which these charts are handy, but you got to have those age dates. So this is one, which we're looking at here. It's hard to see all this, but what you have here is a relative sea level curve with high stand of sea level to the left, low stand of sea level to the right, and you can see all the symmetrical cycles here. We've been talking about one cycle and then multiple cycles. So here, for example, if we follow this curve, we're getting and this, by the way, excuse me, this curve runs from 354 million years ago to 295 million years ago. That's the ages that have been determined for this stratigraphic interval. And so if we follow up the curve, go up the general curve first, we see an overall fall in sea level and then a rise in sea level. And the turnaround point is right about here. And in this case, it's when you had some tectonic influence, where you had some foreland basin subsidence from this point on, which raised the sea level. So at this scale of the time range is 59 million years, and at that scale you have one fall rise cycle. That's not going to do you much good when it comes to reservoir, so you want to go down to the next cycle down, or the next two cycles down, And you do the same thing that we just did. You superimpose, or what has been done is that the symmetrical curves have been, the higher frequency symmetrical curves have been superimposed on this broader low frequency curve. So now let's say you're in this area, okay, and you want to, like I said a few minutes ago, let's say you want to drill for fluvial deposits. Okay, you want to drill for fluvial deposits. That's your exploration target. Well, fluvial deposits occur at a certain time. That early rise in sea level is when the fluvial sediments are deposited in, say, in Scythe valleys. And so, what are you going to look for? You're going to look for these intervals, right, like that one there, where you've got the low stand and early rise. You can't see it at this scale, but where you've got the very early rise, the vertical axis here is geological time. So now you have, for your area, you have knowledge of the sea level cyclicity and at what specific time intervals, geologic time intervals, you might find fluvial deposits to drill for. So the next thing is you go back to a well, or you drill a new well, or let's go back to the older wells, and you do some biostratigraphy and on the cuttings, and you pick out some fossils and you can age date. So if you happen to get an age date that falls in that time period where you know that you had that turnaround fall in the fall rise cycle, you can know at that horizon, you should, in your stratigraphic section, you should be able to find fluvial deposits. So, great exploration tool. And as I showed, at the higher frequencies, very good for reservoir characterization and for correlation. So this is just part of this, the hack curve that I called before, this guy named Hack. This is a project that one of my grad students and I did, where we took the hack curve for this time interval that we were working in, and we just superimposed it, and we see that falling stage and turnaround and rise. Now in this case, what we were looking for was submarine fan deposits. And the name of the formation of submarine fan deposits in this area was called the Jack Fork group of rocks. So where are we going to look for the Jack Fork group? Well, we're going to look where we have the low frequency fall in sea level. So we would look in this interval, about in there. And then we would look at that next higher order of cyclicity, and wherever you have a falling stage, that's where you're going to most likely have your submarine fan deposits. When you have the high frequency falling stages of sea level, in this case superimposed upon superimposed a lot in a higher frequency, lower frequency fall in sea level. So sure enough, here's the Jack Fork group. Well, we were able to date from fossils. We were able to date the Jack Fork group as being deposited about 323 million years ago. Okay, 323 million years ago. At that time, you had tectonics, which helped to increase the supply of rocks, uplifted rocks, that increase the erosion and source of sediments that went out into the basin that formed the Jack Fork group. So there it is there, big submarine fan deposits. I take my students out there every semester in this area. And we know the age range, we know how many cycles there are, how many sea level cycles. There's all these cycles, high frequency cycles within that geologic time interval. Just the Jack Fork is only represents about this time interval, but these other formations that are shown here, there's lots of fall rise cycles of sea level. So, Bolivia, somewhere you probably in your company somewhere, I'm betting that there's a one of these curves or one of these charts, and they can guide you to new exploration areas. If you take some of your reservoirs and you can age date them with the fossils, you can then go to new areas where you do have a little bit of age control and pick out those geological time intervals where you're apt to get the same reservoir. So it's a very good primary exploration tool. Let's see where I am here. I kind of skipped some things. Oh yeah. Okay. I'm going to talk a little bit now about going into some more of this biostratigraphy and talk about it a little bit more. So here's the biostratigraphy. Whoop, excuse me. Here's the biostratigraphy. I've gone back a little bit now in this lecture, my pictures. And it's important to sequence stratigraphy. And one of the big importances, well, is first of all is the source rock, hydrocarbon source rock. Well, yeah, condensed sections are hydrocarbon source rock. They're seal rock. And they're pretty easy to identify, particularly if you've got biostratigraphy. So they're very important. They're also important because they're good regional stratigraphic markers. Very high gamma ray shales because of all the organic matter, and so they make good regional markers. So really, when I do a project, and I think I've said this once or twice before, when I do a project, it's the reason first thing I ask for is the biostratigraphy report, is so that I can use that to try to find the condensed sections. Okay, and then the condensed sections become my correlation markers from well to well. So, biostratigraphy is an essential tool in understanding depositional systems at the regional scale. It allows you to establish a chronostratigraphic or sequence stratigraphic framework of the sedimentary basin. You can get specific age dates. From that you can estimate sedimentation rates, and you can do regional correlations. At the field scale, the development scale, what we would call high resolution biostratigraphy, that's looking in more detail, can be helpful in correlating specific reservoir sands. Okay, so let's look at these a little bit. And now I know you guys work mainly with non-marine, but you don't find many fossils in the non-marine. I'm going to talk in terms of marine microfauna. If you're working in any shallow marine or coastal type settings, then you will find marine fauna, and the micro means very little. They're about the size of pinheads, millimeter-sized organisms that lived in the water column. And there's two groups. One called planktonic. These are organisms that float in the water column. So here's a little cartoon of the seafloor. All these planktonic organisms floating around in the water column, and they live there until they die, and then when they die, they fall to the bottom and get mixed up with the sediments. So they get incorporated into the rocks ultimately. Now, benthonic ones, by contrast, are ones of microorganisms that live on the bottom. They live on the seafloor. That's these ones that are illustrated down there. Well, just to show you what they look like, here's a jar full of salt seawater, and I was on an ocean cruise. I used to be a marine geologist early in my career, and we used to go out on these marine research vessels, ships, and when you go out on one of these research ships, they're expensive. And so you try to take a lot of people, a lot of different disciplines out on these ships. So I was a marine geologist looking at the bottom sediments. We had biologists, marine biologists, a chemical oceanographer that looks at the water chemistry, stuff like that. And we had the biologists there that were collecting plankton samples. And so they had these nets that they would tow along behind the boat and periodically bring up the net and scoop out all of the microfossils. Well, one day I asked them, I said, can you bring me a jar full? Because I've never seen a live plankton. I've seen lots of dead ones under a microscope, but I've never seen a live one. So they said, sure. So they brought me up a jar, and if you can see these little specks here, those are the microfauna. These are the plankton. Okay, they lived in the water column and got trapped in the jar. If you listen closely, you can hear them say, help me, help me. Well, it didn't help them, and they all died. They started to fall on the bottom here. Once the water warmed up a little bit, it was out of their environment, so they died. They were screaming all the way. So that's what they look like. And then when they die, they fall to the seafloor and they get mixed in with the sediments. And that's what you look for in your cuttings or in your core. Well, there's hundreds and hundreds of different types of these planktonic organisms. And you have to really be a specialist to be able to look under a microscope and see these organisms and identify them. And so here's just a picture of some of the different types that you might find. And you can see different shapes and so on. And like I say, you got to be a specialist to identify them. Well, a lot of these fossils evolved and then became extinct over long intervals of geological time. So those aren't very good for helping you define the age at which a particular sediment was deposited in a well. What you want to have is organisms that had a relatively short time span, where they evolved and then became extinct very quickly in a short time interval. And those are the ones you want to look for, and again, you got to be a specialist. Now, all the ones shown here have a very a long time range. For example, I don't know how familiar you are with geologic terms, but this one here, for example, started to evolve way back in the Silurian, hundreds of millions of years ago, and is still living. Not the same organism, but the same species is still living. So it's not any good. You can find a lot of those in the sediment, but it's not going to be, all you can say is, well, it's between Silurian and recent times. But if you find some, and what you look for again are ones that have a short time frame. Now, most of these here have a long time frame. I guess this is probably one of the shortest ones, Devonian age to Permian age, and that's still a very long time frame. This one's lower and middle Permian, that's a little bit better. But you want ones that lived in or evolved over a short time frame and then became extinct. Well, how do you look for these sorts of things? How do you find these little organisms that have died and fallen in with the sediment? They're if you just look at the sediment, core or cuttings, you never see them, even under a microscope. They're just too small, and they're not in that great an abundance. So you have to prepare your sediment. So what you do is you get your cuttings from the drilling platform, and you wash the mud off, the drilling mud off the cuttings until you get nice clean cuttings. And here's some picture of some nice clean cuttings. And they're separated by the depth at which they were drilled. And in this case, the depths were at 10-foot intervals. So this is 1,050 feet, 1,060, 1,070, and so on. So you've got an interval in these cuttings of 10-foot interval. Well, you look at those clean cuttings and you look under a microscope, and it's really very difficult to impossible to see these organisms. So what you need to do is somehow figure a way to concentrate these organisms. And the best way to do that is to dissolve out the mineral matrix, the mud matrix, or the sand matrix. In this case, well, no, let me take that back. You wash out the inorganic material that makes up the cuttings, the clays, feldspars, quartz, things like that. And then, if you can find a chemical reagent that dissolves out the quartz and the feldspars and all that in the clays, but does not dissolve the microfauna, then what you can do is you can put your sample into the chemical reagent, let it sit overnight. It dissolves out all the cuttings pieces, and when you come back in the morning, you've got a little pile on the bottom of pure microfauna. Then you can see them. Then you can wash the reagent off and look under a microscope, and a specialist can do that and tell you what sort of fossils you have, identify them. And it's pretty easy. The chemical agent that is used is usually hydrofluoric acid. Hydrofluoric acid will dissolve quartz and feldspar and clay minerals, but it is unreactive to the mineral calcite. And most of these microfauna have calcite shells. Okay, so you don't dissolve them. So you put your sample, your washed cutting sample in the hydrofluoric acid, in a beaker or something, let it sit for overnight or something, come back, and all the mineral matrix will have been dissolved, and you'll just have a little pile on the bottom of the calcite shell material. So that's how you do it, and that's how it's done in these paleontology labs. So what do you do once you've gotten to that point? What do you do then? Well, you then, the specialist starts looking under the microscope at all these different intervals where you've got all of the microfauna. interval here, interval, in that last case I showed you every 10 feet. Okay, so every 10 feet you're looking at a set of microfauna that were deposited in that 10-foot interval in your stratigraphic column, in your reservoir. Well, you can't really read this. I'll just tell you what you've got here is a whole bunch of, this column up here is a whole bunch of Latin names for individual microfauna. And the vertical scale here is depth in a well. And so wherever you have a check mark here, that means you have found a particular one of these microfauna at that particular depth. So for example, I have a little check right there. So that means this organism right up here, I found that at that depth. And so at two different depths I found that organism, but then I went further down in the well and I didn't find it anymore. Well, what that means is that, remember, you're getting younger in geologic age as you go up the stratigraphic column. So what that tells you is that that's a really good fossil to use for age dating, because it must have had a very short time span that it lived, that it evolved and then became extinct, because you don't see it throughout much of this set of cuttings. Now you look at this one, for example, this organism, and you find it in almost the entire interval, entire well. And so you identify that in all these intervals. That's not going to be a very good age discriminator because it must have had a long time span from evolution to extinction. So you look for these things, and if you've got more than one well, for example, let's go stick with this where you have this here. This organism in just two of the intervals, and nothing below and not above. And let's go to another well. And in the other well, you find the same thing. You find these two organisms, or this one organism, only in a very restricted stratigraphic interval. Well, you can use that to correlate. So you can go from one well to the next just by identifying these microfauna, particularly the ones that have a very restricted age range. Now, paleontologists have done and biostratigraphers have done a very good job through the years at being able to find the absolute ages at which a lot of these organisms live. There are ways to do that I won't get into now, but paleontologists and biostratigraphers are very good at having been able to figure out when a particular organism started to evolve and when it became extinct. So there's a good likelihood, for example, that we know the absolute age of this particular organism that you only see in these two intervals of the cuttings. So you know the depth, you know the age, and so you have that piece of information. If you go to another well and you find the same sort of thing in the other well, you can age date that well too. You can provide that age at which you find this organism to that well also. Now let's go back to this picture. Go back to All right, so I'm going to go back to this picture I showed a few minutes ago. So if now in one well, I know the age at a particular horizon because that's where that organism was found, and we know the age at which the organism evolved, then if I go to another, then I can go to my sea level curve, my relative sea level curve, and I can look for that age, and we'll say, just for the heck of it, we'll say this age right there. So then I can look for the same type of rock in this area that I had where I drilled the well and was able to determine the age. I could correlate to another well. Okay? So that is some of the value of this. So let's see, let me go. Okay, so we're up here. Let me give you an example of that. Okay, well here's a picture you can't read at all, but that's all right. I'm going to tell you what it is. It's similar to the last picture in that the horizontal axis are different organisms. You can't read this, but it's all those little Latin names of these different species of organisms that you may find in your area. The vertical axis is depth in a well. So let's see how we can use this information to age date the timing of deposition of our reservoir, of our sedimentary column. Well, let's, for example, let's look here. Here's a fossil. You can't read the name of it, but here's a fossil that was found at intervals up to all the way down, and up to there. But you didn't find it above that interval. Well, what that must mean then is that that particular organism lived down here all the way up to here, and then it became extinct. Let's look at another organism. This one, you don't really see it below this depth here, and you don't see it above this depth here. So it evolved at whatever age is represented by that depth, and then became extinct right up there. Take another example, take one more. Here's another organism that living down near the bottom of the well, the stratigraphic section, and you get up to here and it became extinct. You don't see it above any the shallower depths anymore. Well, let's say now that we know the ages at which those organisms became extinct. So what I've put on here is that we know that this particular organism, we know from past studies, that this organism became extinct 500,000 years ago. Okay? After 500,000 years, you don't find it anymore. So it must have become extinct, that species of organism, became extinct 500,000 years ago. Let's say we have this organism here, whatever it's called, and it became extinct 750,000 years ago. And we have learned from past studies that that particular organism started to evolve, first came into appearance 1.2 million years ago. So now we have a range here. We have an age date. And again, I think I said this is depth in the well, the vertical axis. So I now have an age date at a particular depth, and another age date at a deeper depth, and an age date up here. So I've now got 3 age dates, actually 4, because this organism started to evolve 1.5 million years ago. So we have 1 million years ago here, okay, because that was your extinction age there. We've got I have one in here that shouldn't be here. Oh yeah, 1.2 million years old is when this organism started to evolve. Okay, so we now know that we've got 200,000 years of deposition between this depth and that depth, between the two green lines. 200,000 years of deposition from 1.2 million years to 1.0 million years. We can do some more. If we know that this depth in your well is was deposited 750,000 years ago, so we now know we have an interval here from 1 million years ago to 750,000 years ago, or 250,000 years. And we could do the same thing up here. We've got a 500,000 and a 750,000 down here. So we know this is 250,000 right there, time interval. So what? What's the importance of that? Well, part of it is that if you have periods of deposition where the rate of deposition is high, you're more apt to find sand than in an interval where the depositional rate was slow. Perhaps the best example of that is the condensed section, which generally is a slow sedimentation rate. It's very thin and it's shaly. Whereas you take a big drop in sea level or have some tectonics and you get a high sedimentation rate. So by having these age dates, you can calculate out the sedimentation rate. So for example, if you've got 500,000 years here and 750,000 years here, that's 250,000 years. So this interval was deposited over a time span of 250,000 years. This one down here, from 750,000 to 1 million, same thing, 250,000 years. This one now, 1 million years, 1.5 million years. So now 500,000 years. So which has the highest sedimentation rate? Well, the ones where you have the thickest interval and the least amount of time is going to have your highest sedimentation rate. More sediment deposited over a small time interval. So, if I have a well where I've established some of these ages, I can say, well, let's see now. Where do I want to look for intervals that might have a lot of sand in them? Well, I'm going to go down here because the sedimentation rate was much higher. Wait a minute, excuse me. No, that's wrong. Got that backwards. I've got to go through one more thing here. Okay, I had that back the other way around. So here's kind of a simplified version. Here we found of a well in the Gulf of Mexico, and we found these ages: 0.8 million years, 1.2, 2.2, 2.8, 3.5. Well, that is part of figuring out the sedimentation rate. But there's another part to that, and that is knowing the thickness of sediment that was deposited during that time interval. So, if, for example, at 0.8 million years, you were at a depth of 5,800 feet in your well, and at 1.2 million years, you were at a depth of 6,700 feet in your well. So what is that? That's 900 feet. Okay, 900 feet. And the age right at this horizon is 1.2 million years. So what you're saying is you had 700 feet of sediment, or 900 feet of sediment deposited over a 0.4 million year time interval. That is a rate of sedimentation. Now in geology it's big terms, you know, big time intervals, but so that example I just gave you is shown here. The interval sedimentation rate is a function of the thickness of the interval divided by the age at the top of the interval and the age at the age at the bottom of the interval minus the age at the top of the interval. So in that example, where you had the bottom was at 6,700 feet, right there, and the top was 5,800 feet right here. The age range at the bottom was 1.2 million years. The age range at the top was 0.8. So you divide 900 by 0.4 million years, and your sedimentation rate comes out 2,250 feet per million years. You always convert these to millions of years. So even though your actual sedimentation only took place in 400,000 years, you always standardize by going up to 1,000,000 years. So 400,000 would be 2.5 times. 2.5 times that would be 1,000,000. And so that gives you 2,250 feet per billion years. Kind of complicated, but once again, one of the things you can do with this then is, let's take one more of these intervals here. Take this one down here, and the bottom of that interval was deposited 2.2 million years ago, and it's at a depth of 9,000 feet. So we've got 9,000 deposited at 2.2 million years. (9,000 feet) over 2.2 million years. And up here you have 6,700 depth at 1.2 million years. So you just, the interval thickness is going to be 2,300 feet. Over a time span of 2.2 minus 1.2 or 1 million years, so that's 2,300 feet per million years. Now that's a higher sedimentation rate than this interval here. Okay, this interval had 2,250 feet per million years. Now you've got just a little bit more. Even though the thicknesses are different, you had different sedimentation rates, and so you have different ages. And here the ages are closer together, and here they're wider apart. So where would I want to go to drill or to look for more sand? I would want to go and look in this interval here because it's got a higher sedimentation rate. So that's one of the things that you can do with this, or calculate the sedimentation rate when you have the ages. All right, well, let's go back to this diagram here. And here we've got our planktonic organisms living in the water column. And they live there and they die there. They don't really care what's going on the seafloor. These benthic ones, they live on the seafloor, so it really matters to them what's happening. But the planktonics are in the water column. They don't really care what's happening on the seafloor. So they they live and they die and they fall to the seafloor at kind of a constant rate. Well, if you are in a time interval where you're having a low sediment input or a low sedimentation rate, those organisms, as they die, as they die and fall through the water column and ultimately get mixed in with the sediment, you'll get a certain amount of fossils per volume of sediment. Suppose, though, that you have a very high sedimentation rate, so you're bringing in a lot of sediment over the same interval of time, so you have a high sedimentation rate. Well, you're still going to have the same number of organisms falling through the column, because they don't care what happens down on the seafloor. They're dead by then. And so they mix in with the sediment when they fall to the seafloor, but their concentration is going to be much lower. Their concentration is going to be much lower in terms of the volume of these microfauna over the volume of the total rock mass. So, what in practical terms, what you would like to do, what you would like to be able to do is find those intervals at which you had a very low sedimentation rate, because then you're going to find more of a concentration of these organisms than in an interval that had a high sedimentation rate. Where do you get a low sedimentation rate? You get that in your condensed section. very fine-grained sediment in your condensed section. Your condensed section is shaly. It's got a lot of organic matter, so it gives you a high gamma ray kick, too. So, let's look at a depth chart again. Depth here. And here we have a depth chart where a paleontologist went through and looked at every sample and determined that looking at just the planktonic organisms, that there were certain intervals where you had a high sedimentation, or you had a high abundance of the planktonic organisms, and then you had intervals where you had either low abundance or no abundance. Well, there's another type of organism that I haven't talked about called nanofossils. It too is just a very fine-grained one, and you see the same thing. You get certain intervals where you have a greater abundance than in other intervals. That's shown by these curves. Well, going back to this figure, which of these figures here, the upper one or the lower one, are you going to get the high concentration of the organisms? You're going to get it in the lower sedimentation rate, which is your condensed section. So, to define your condensed section, these are all condensed sections. So now we've identified, in this particular well, 6 condensed sections. And if we know the ages of them, we've got 6 ages that we can use to establish our sedimentation rates and find out when you had periods of high sedimentation and when you had periods of low sedimentation. Well, that's fine, you know, if you're doing exploration, but it's fine if you're doing exploration, but most of your exploration, and nowadays a lot of your development, your reservoir characterization, is done using seismic. So what you really would like to do is find where these different condensed sections are on seismic. Remember, you want to identify the condensed section because they're the hydrocarbon source rock and they're a seal rock, top seal, or a seal rock. So what you'd like to do is put this onto seismic. Well logs are in a depth scale and seismic is in a 2-way travel time scale. But it's pretty easy to convert one to the other. There's standard computer programs that you input a little bit of data on the rock type, on the petrophysical properties of the rock, and you can do a conversion from depth in a well to 2-way seismic travel time in a well. Once you do that, and that's what's been done here, we went from depth, and we converted that log into, I'll call it an amplitude log, a seismic amplitude log. And, well, this is the column I really need to show. This is the one that shows the high abundance peaks of these organisms. So here you had a high abundance peak. Here you had one. Here you had one. There's one, and then a big one down there, and a little one over here. Okay, now, once we've done that in depth, now we do our conversion to 2-way seismic time, and we generate what we call a synthetic seismogram, or a 1D seismic model. So we've gone from depth in a well to depth in 2-way seismic travel time, and how it is expressed here then is where you get this high abundance peak. That's a condensed section, and here it is right here. It's this amplitude. It's that reflector. Here you see a series of or a long interval of condensed section, and what do you see? You get a bunch of reflectors. Not always does that work. You don't get much here. You do get a reflector there. But anyway, so the point is that what I've done here is I've gone from the finding the condensed sections on well logs, and I've converted that to finding the condensed sections on seismic. So now I've got a real handy tool that I can map these condensed sections around using seismic, and that's how I can correlate. So taking one example, here's a 3D seismic survey with some wells. These are deviated wells. Well 1, well 2, well 3, well 4. That's 3 sidetracks here. Okay, well, here's one of the seismic lines from that 3D seismic survey. Now, what I said here was that you can convert log depth into seismic two-way travel time. Well, you can also do the reverse. If you've got a seismic section, two-way travel time, you can convert that to depth in feet or meters. And that's in this particular case I'm showing you, that's what was done. So now we're looking at our vertical axis in depth. 5,000 feet here, 2,500 feet, 10,000, 7,500, and so on. Now we can superimpose our well, and wherever we find one of these high gamma ray peaks, which is the condensed section, we can tie that to a seismic reflector. And that's what we've done here. These green lines are condensed sections. They represent condensed sections. So by calibrating at one well, and then going to your seismic, you can then do more regional mapping of your, in this case, your condensed sections. You can do the same thing with sequence boundaries as well. So if I'm looking for condensed sections on my seismic, because I want to know how much source rock I've got. Okay, so I want to see how many condensed sections and where they are. Well, I go to my well log, and here I've superimposed the well log at the same scale. And I go to the well log, and wherever I find a high gamma ray peak, that's going to correspond with a condensed section. One there, B1 there, and so on. Well, we give names to these condensed sections based on the key fossil that is found in that condensed section. And it turns out that this condensed section, which is shown by this high gamma ray peak here, is the organism that you used to identify that was called Lacanosa, another one of these Latin names. And we know then by superimposing the well log with the seismic section at the same depth, we know that Lacanosa occurred right there. So now, we've got a condensed section that we've tied to a seismic reflection. And so we can start mapping that around, like that. And we look for another one, and I'll just show one more down here. You see that nice high gamma ray peak there. That's another condensed section, and the organism by which it was identified is called Gyrocapsa. It's another one of those Latin names for an organism. And that one occurs right down here. Now, we happen to know the ages at which those became extinct. So we can now add ages onto this. But more important, I think, is that what you have been able to do now, there's another one here that I didn't bother to mention. What I can do now is I can look for my source rocks and I can map them around. Okay, and they're going to be mapped around this interval right here, the condensed section. Now, if you, let's do this. If you're, by our sequence stratigraphic model, our condensed section is going to have the maximum gamma ray log response. So you'll have something like this, okay, where sand here and shale there. And you get this nice high gamma ray kick, which indicates your condensed section. Well, from our geological model that we've been working on all day today, our stratigraphic model, what should occur beneath the condensed section? We mapped these out before. Well, let's say first, what should occur above the condensed section? Remember those downlapping reflectors onto that condensed section? So you're going to have above the condensed section, you're going to have your high stand deposits. What you have below the condensed section depends on if had deposition of your reservoir in shallow or deep water. If it was in shallow water, you're going to have one of those transgressive surfaces of erosion and your condensed section right above it. If you're in deep water, what are you going to have beneath the condensed section? You're going to have submarine fan deposit. So now I really got something that I can work with, because let's say that your boss says this year we're gonna explore for deep water sands. Okay, forget about everything else. And so you look at a seismic line like that, and you say, well, gee, where am I going to look for these sands, these deep water sands? Well, if you've got this much well control, you can predict, because in deep water, below the condensed section, you're going to have submarine fans. So where are they going to be? If this is your condensed section, your submarine fan's going to be right down there. If you've got a condensed section here, your submarine fan's going to be right down there. If you've got a condensed section here, your submarine fans are going to be down there, and so on. So, suppose the boss says, this year we're going to look for submarine fans, but you've only got till tomorrow to figure it out. And you say, well, gee, look at all the lines. I got this 3D survey, and, it's going to take me a long time to interpret one line. Well, if you've got this bit of data, let's say one well log, that you can calibrate some biostratigraphy, and where you see your condensed section, then you can narrow down substantially where you're going to look for, what interval you're going to look for your submarine fans. Not only that, but you have a bonus. Because you go in the morning and you tell the boss, not only did I find a whopping big submarine fan that's very high amplitude, meaning really good sand, like this one it's not showing up there, but this one here, whopping big submarine fan with lots of high amplitude reflectors, which is fairly typical of submarine fans. But not only that, but I found the seal and I found the source rock. So that's the bonus. So right here in this interval, you've got reservoir. Beneath the condensed section, you've got the condensed section, which is the seal and the source rock. Okay, so that's how you can interpret seismic. You can, like I said at the start this morning, you can interpret, you can do a sequence stratigraphy without a complete data set. In other words, in a lot of areas you may not have a well, you just have seismic, and then you look for certain patterns on your seismic that tell you when you've got a submarine fan, or when you've got a condensed section, or when you have an incised valley like we've been looking at yesterday and today. So but the more data that you have, the more robust will be your geological model. But for example, I wouldn't waste my time if I only had one day to figure out where the deep water sands are. I wouldn't even waste my time here. Because I know I've got a condensed section there, I've got a condensed section down there, and that's going to be probably high stand mud, something like that. Yeah, that's right. Well, I hate to bring this up at such a late time in the day. Let's just see if I can hold this off till tomorrow morning. Well, I'm going to go through these last few slides. This is a little bit more complex, but while we're getting all this complex stuff out of the way, we may as well finish it off. Okay, like I said, most basins and most areas in the world have these charts that have been put together. Well, here's another type of chart. This is done by a company, and this particular chart is specific to the U.S. offshore Gulf of Mexico. The name of the company is called Paleodata, and they have a bunch of experienced paleontologists that have worked in the Gulf of Mexico for many years, and this company hired them all away and said, let's build a chart, one of these sea level charts or biostratigraphy charts that can be used then by everybody working in the Gulf of Mexico. And so they came up with this, and I'm just showing you a small part of this chart. I want to end the day by showing you how to read this, and it gets a little bit complicated. So I'm just showing you part of this chart for part of the stratigraphy in the Gulf of Mexico. Vertical axis is geological time. Here it is here, geological time in millions of years. So 1 million year, 2 million years. So this is just one part of the stratigraphic column. What you see here is these funny Latin names again for different types of planktonic organisms, and where their last appearance, where their last appearance was in the rock record, and what the age was that it became extinct. So, for example, if you can see this funny named organism called Globicalia flexiosa, the number in parentheses is in hundreds of thousands of years, millions of years. So this is 0.1 million years or 100,000 years. That was the extinction age of Globicalia flexiosa, and in the Gulf of Mexico it's very shallow. It occurs very shallow in the stratigraphic section. We go down, and down at this level was the extinction, the last appearance of Globigerina trunculinoides, and it became extinct 0.5 million years ago. Another one, Sphirodeniella, whatever, I don't know the name of that one. But 1.02 million years ago, it became extinct. Another one that I can't pronounce, 1.59 million years, and another one 2.2, and then 2.3. So now we have a series of horizons that we know the age at which the sediment at that horizon was deposited. Now, we would like to build a sequence stratigraphy, but you say, I only spent 2 days in a class by Slatt talking about sequence stratigraphy, and I haven't used it for 6 months, and so I forget it all. And so what can I do? How can I develop a sequence stratigraphy without having to take that class again and go through all that stuff again that's complicated and so on and so forth, and listen to him all day again for a week? And that's why these charts are made, so that you don't have to physically develop a sequence stratigraphy framework yourself. This is a chart that also gives you the sequence stratigraphy for that age range in the Gulf of Mexico, down to about 2.5 million years. So the tricky part now is these triangles here. This is what's hard to explain. I'm going to try to explain what those triangles mean. I'm sure engineers they have equations for all this, but us geologists, we like pictures. We're picture people. So what you see is a triangle here. And the way that triangle was, what it's supposed to mean is the vertical axis is geological time, with the older time here and the younger time there. A rising sea level, with the rising sea level, the triangle will be pointing towards a rise in sea level, and the opposite of that point of the triangle will be a fall in sea level. Okay, so that's how you read those triangles. Most geologists, never got past Algebra 1. So I won't tell you how many times I had to take Algebra 1. So we like these pictures. So let's apply this now. So you've got an older age, younger age, sequence boundary, maximum flooding surface, the maximum rise in sea level. So that's your maximum flooding surface. And your condensed section is going to be just below it, below that surface. Well, here's just another one of these showing the same thing. Okay, so let's go to the picture now, the chart, and see if we can read this chart. Let's just start right here, for example, and you see a triangle going this way. That means sea level is rising, and your maximum sea level rise is where your maximum flooding surface is going to be, and we've age dated that at 1.62 million years. And then we have a fall in sea level, then another rise, and that rise has been age dated at 1.36 million years. Another fall, then another rise, fall, and so you get these kind of like teeth. And what the teeth represent that's what the teeth represent: rising sea level to the left, falling to the right. And so rising sea level to the left, falling sea level to the right. During the rise, you get maximum flooding surface. During the fall, you get a sequence boundary. And you've got a series of ages, extinction ages, at different depths. So now all you got to do is, let's just use this as an example. Lacanosa variety went extinct 0.8 million, 800,000 years ago, 0.8 million. Does that occur where you have a condensed section and maximum flooding surface, or does that occur where you have a sequence boundary? Well, I've drawn the line across here. It occurs where you have your maximum flooding surface, where you have that point in the triangle. So we've now identified one maximum flooding surface and condensed section, which is your source rock and your seal rock. Where are you going to find your reservoir rock? For example, you're going to find that on the falling stage of sea level. So that's the other part of the triangle. So submarine fan deposit, we'll say, and condensed section and maximum flooding surface there. And we've age dated those. If you look very closely at these age dates, you will find that almost all of these age dates correspond to condensed sections and maximum flooding surfaces. Why is that? Because, like I said, during condensed section deposition, it's a slow rate of deposition, so you get a relatively large amount of these organisms in a thin column of sediment, and so they become concentrated, and they're easier to find, and so that's why you find high abundances of microfossils within the condensed section. So you can go along now, and what has happened is your sequence stratigraphy has been developed for you. All you needed was, a well, for example, with some age dates, one well, and then you can go to your local chart, and for example, in the Gulf of Mexico, you can walk into a store, and buy one of these for a couple $100, something like that, and you know then at what depths and at what times you had your rises of sea level and the falls of sea level. So to finish this off, I'm just going to use 3 examples. Lacanosa variety. We know the depth and the age of extinction. Gyrocapsa, and the third one called Selli, S-E-L-L-I. And we have ages, 1.35 million years there, 1.15 there, and 0.8 there. We know that that they are basically, they occur as condensed sections and maximum flooding surfaces. So we go to a well, and we go to that well, and we find at which depth we have Lacanosa, which depth we have Gyrocapsa, and which depth we have Selli. Okay, so now we've got ages that we can put on our seismic section. And when we have that, we can then calculate sedimentation rates, or if you know at what particular geological time interval that is a reservoir interval, and you want to explore for that interval, you can go to this and put your ages onto the seismic section and then map around that particular interval. Well, that's a good place to quit for the day. Usually this lecture is better in the morning than in the afternoon. And I apologize, it's kind of complicated, but early tomorrow morning, the first thing I'll try to go